Okay. Yeah, actually, I'm talking about the real time. That's where the word came from initially. And I'm also talking about history, because kind of like mutated to talk about like the evolution of GRiSP. So let's start in the prehistoric, just starting to paint. So that's where it all started. That's a device. I can actually say I built because I didn't have employees back then. And that's what got me started with Erlang, basically. Because this was supposed to be a network device that flashes car ECUs. That's the little control boxes that go in the car. And I read in a magazine that there's this language was built in distribution. And I thought, oh, maybe I'll try this out. It's kind of like boring to like write the new version because this is version 3. The new version in C again, even if I can use a lot of code, but kind of like got fed up with that. So let's try out this Erlang thing. And well, 1 month in, that was my point of no return, like going back to the old code base. There was no going back. No way. Because I made so much progress. This is like, I really loved it. And that was while I was actually learning the language. So this was pretty cool. So the way this looked is that there's a normal PC mainboard, like an industrial mainboard running FreeBSD and Erlang, kind of like in a nerves-like setup, you would say nowadays. Just using FreeBSD and NanoBSD. And there was like the hard real-time stuff was running on specialized hardware that we built, which also provided us access to all the car field buses that exist, which there are many. So all of those implemented in Erlang. I can say this would not have been possible in any other language for a single developer to develop all these bizarre protocols, because they are really bizarre, some of them. Like most is the worst. It's the most bizarre protocol I ever saw. Actually, I'm not sure because I saw other bizarre protocols, but yeah. It's one of the top bizarre protocols. It's optical, it's for audio and all kinds of, then they put all kinds of other shit on top of it, and then you have layers of shit on top of it. Yeah. BMW invented it and they killed it again. Like, yeah. So that's where it started, but that was not GRiSP yet. But it was kind of like an embedded thing, so let's go a little bit more in the future. So there was this thing, like industrial manufacturing. So one of my long-term customers is Bosch, like in Robert Bosch, not Porsche, but Bosch. It's kind of like confusing in English. And they make like conveyor belts and industrial manufacturing things. And if you look at this little circle, there's 2 little boards there with like green wires coming out of the top. And that's kind of like pre-GRiSP thingies. So that was like a specialized hardware for Bosch that in a networked way, because we had this distribution thing running, so there's 15 boards on this conveyor belt thing that run a distributed control system that runs all these movements. Everything that's moving is controlled by these little boards. By the way, nowadays, these run GRiSP. So we basically backported the GRiSP stack to these boards also. So they started the whole evolution and they got it back, which is like how open source is supposed to work. Somebody, like some customer pays for something and then they get it back because they profit from the evolution of the thing. So that's another picture of the thing, so like 3D interfaces, but it's really small. It's only the top thing is actually the PCB. The lower thing is just for wiring. So that's kind of like GRiSP 0. Well, actually, I shouldn't call it GRiSP 0 because we might do a GRiSP 0, like Raspberry Pi 0. I need to be careful about that. So here now, yeah, where we are. So actually, it's kind of like just in the here and now, because the demo is still with GRiSP 1. So I won't explain everything about the board. So we used to have like a bunch of slides where we explain all the parts on the board. So that's how it looks. You see the 3 boards hanging up there. You have these black things on the top. That's so-called P-mode connectors, which are these little boards here, like stuff like this size of boards. And you get like hundreds of sensors and actuators for those. And they have different kinds. There's GPIO, there's UART, there's SPI, there's I2C, there's a Wi-Fi on the board. We have an SD card to boot from. CPU about 200 megahertz or 300 megahertz actually. Effectively, it's actually running with 100 megahertz because you needed to work around the bug in the USB chip. that kind of like was annoying. That's why we don't use the CPU anymore in GRiSP 2. Yeah, like showing you a few more P-mods. So the motor one, that's a motor driver basically. So you can attach a battery and then you can let this motor run forward and backward and set its speed. You get sensors, radios, motor controllers, everything. And also, what's very nice, if you want to go into hardware, building a P-mod is a very nice first project for hardware, because it's a very simple mini PCB, and you can also hand solder them. I have several things where I got some other module and rewrite it on a grid thing and made a P-mod out of it, like P-mod-like thing. It's a very simple interface. So it's really beginner's projects. So that gets me to my first demo. We have 2 demos if you have time for it. So I need to re-plug this into the laptop. I hope this works. Hello? Stuff happens. Oh yeah, this worked. So on these little critters, I prepared something. So this is not like doing from scratch. So it's actually running something already. It's running the base GRiSP application. And this code that you can see here, actually I need to make it brighter again because I dimmed it down. So actually now the mouse is gone again. Or I don't see it anymore. Oh no, it's still here. It's just too dim. 1 second, I need to make this brighter because I dimmed it down so it actually would run on battery and not drain. So now I can see something also. So this little code I wrote yesterday, it's just a gen server. I hooked it up into the main supervisor of the thing, and it kind of like initializes, switches off all the LEDs, that's why they are dark. And then you can set a next node. So these are distributed, these Erlang nodes, and I have a little Wi-Fi base station brought myself here, because usually you can't use Wi-Fi's because they don't let, like hotel Wi-Fi's or conference Wi-Fi's, they don't let interconnections between 2 devices. That's for security reasons, it's usually blocked nowadays. So I always need to bring my own Wi-Fi thing. So these are running, and this little gen server, basically you set a next node, and when I send it a ping message, it's supposed to send the pin message to the next node. And before it does so, it's supposed to flash the LED, and that's this line here. So if it gets a ping, it sets the LED blue for 100 milliseconds, then it sends out the ping, and then it switches off the LED again. So what we are supposed to see is like a blue light going like in circles by message sending over Erlang distribution. So let me get my right window. So the blue one is a remote shell that's connected to one of the boards, the middle one actually. So I need to, that's a problem. I kind of like restarted this. Where's my, let me get my little window to cut and paste from. So I didn't make a nice API to get it started, so we basically just call the gen server cast. So let's make it larger so you see what I'm doing. Can everybody read this? Okay. So I sent the first one a ping, and then let's see what happens. Does it work? Yo, this is Erlang distribution running. It's a little bit jerky because the radio range is not very good between these things. But it works. So yeah, well, that's kind of boring. So let's change the code on the fly and do some hot code loading. So what if we want the color not blue but yellow? And well, so you can actually see it better, let's actually switch on both LEDs. And switch off both LEDs because otherwise it gets stuck in one LED. So let's save this, and so I'm supposed to have my little, so there's a little other window here, the red one. So that's what I usually call a loader node. So that's an Erlang node running on my laptop which already I kind of like prepared this and pinged all these nodes so that we don't have to do it now. So if I do nodes now and everything still works, we should see actually MPEG 8 GRiSP 100, MPEG 8 GRiSP 222, and then R1 Venus is my remote shell on my laptop, which is called Venus, and then MPEG 8 GRiSP 251. So that's all the nodes that I'm connected to. And I'm in the source directory, so I compile the module. So that's compiled, and then there's a nice little thing, it's called NL in the Erlang shell, netload. And now it's yellow, hot code loading. And so this shows you the productivity you get, basically, because you don't reboot the board, you don't lead everything, you don't load all the booting takes some time, you need to load the code into the embedded system, then it crashes again. So it usually doesn't crash, or if it crashes, the supervisor fixes it, and then you can kind of like iteratively work on your code. So yeah, maybe one little change because that's kind of like boring. Let's make it a little bit more hectic, 10 milliseconds. Compile, netload. So yeah, it's actually working pretty well, Erlang distribution. So let's go back to my iPad again and continue with the slides. Oops. So, yeah, so while this comes up, so since GRiSP 1 is kind of like around for a while, we basically sold off the first batch, and the second batch will be GRiSP 2 already, so it will be a different board. We already did a few things with it, because that's one of the uses of GRiSP, it's our own prototyping board. So for a US company that was, that's into like making trail assessment tools, so these like little wheels with the magnets around the wheel and this little sensor box on top, basically this contains a GRiSP board. And they were kind of like, we got in contact with them because they had a prototype which they kind of like failed doing it. Somebody who was not able to do this did it. And they said, can you actually build this in 1 month, a prototype? Because we kind of like federal funding and we need to show something by the end of the month. And it was kind of like an interesting challenge. So it was really all hands on deck and we really did this. GPS, accelerometer for the leveling, a display, LCD display, which we hadn't before, the sensor for the magnetometers, and a Bluetooth thing to transfer the data to an iPad. 1 month, whole team, like back then, like 3 people were working on it full time, 3 to 4, and it worked. And they're using this. They didn't call back because that's what happens when you write something on the beam. It just works. It has bugs. It keeps working. My solar heating system and heating system in the house runs on a GRiSP board. I know there's a bug in the one-wire driver, and I intentionally didn't fix it on this board. So occasionally it will crash. I know this because when a sensor doesn't read, the driver crashes, which is not good. It's not nice. But I leave this, and it's running since March. And I dare to travel in winter. In Munich winter, it's cold. You need heating and warm water. So I didn't get a phone call yet. So this works. It works really astonishingly well. And it's kind of like scary sometimes. So another project we did, we have this lifter test. That's case lifter in manufacturing. So lifting up cases with a sensor so you don't have to go down all the time, so you can just pick your stuff. And they had quality problems with this thing. And we tried out a pilot project using QuickCheck, doing hardware in the loop testing on the PCB of the lifter, and then on the lifter itself, basically generating a minimal test. I can't go more into that. Actually, it worked quite well. And we used the GRiSP board to attach to talk to the hardware. That's a little robot car. It's the latest iteration of the robot car. Actually, this is a video it's supposed to play. Yes. So that's basically, that was the result of a one-day tutorial. So these 2 guys to the left were in the tutorial, and they started with an empty directory and built this from scratch. Robocar, control it by tilting the other GRiSP board over the Wi-Fi. And what I heard, they had a lot of fun. The little Robocar also has like sensors on it, but we're not using that yet. So that's kind of like, we are trying to build a kit which you might sell in the shop, so you can actually get started quickly with a robot car. Another application, the LightCon research project, the EU research project, which just finished, which we were part of. It's about edge computing, distributed stuff, CRDTs, and all kinds of things around this. And there were like half of the research partners were using Erlang, and they were really happy to get our GRiSP boards inside the project to prototype edge computing on real edge devices. Because then they could run their Erlang code not only on their laptops, but also on real devices. So kind of like another thing we did, which I intentionally put in because it's the real-time conference here. So this is like about the real time. So the normal Erlang VM has soft real-time, which kind of like, the definition of real-timeness is really fuzzy, and there's many meanings, as we all know. That soft real-time, the average execution time is usually below the deadline, and occasionally you can have a worst-case execution time which is beyond the deadline, occasionally. And kind of like, what does occasionally mean? It's probabilities. Like, probability needs to be low enough, and it needs to taper off long enough, well, quickly enough, then it's okay. Hard real-time, worst-case execution time is always below the deadline. So it's an error to actually not meet the deadline. But to be honest, hard real-time is also soft real-time, because it's all probabilities. If your CPU breaks, you will miss your deadline. If you have 4 CPUs that work in lockstep and all kinds of things, well, if one breaks, it's fine. If 2 breaks, it's also fine. But if they all break, or the power supply breaks, you miss your deadline. So there's always probabilities, because the real world doesn't have 100%. So what we did, what happened now? Hello? That's interesting. I have a slide here. Okay. So it tells you don't want to see the slide. I tell you, I keep this slide. What we did is we started experimenting, but because what the goal is, we have a hard real-time system underneath. I will tell you about this in a minute. And what I really want to do is not drop down to C to actually implement real-time stuff, hard real-time stuff. So the goal is to have hard real-time processes in Erlang and Elixir. That's kind of like garbage collected language. But we have a plan, like you do have several deadlines, a short deadline and a long deadline, like a recovery deadline, which model it by a maximum message rate and all kinds of things. And we did an experiment. It was a master thesis of a student who implemented a second scheduler at a higher priority of the real-time operating system we are using. Operating system is quotes. I'm always doing quotes when I say operating system. And it actually worked quite well. But it's only partial way. So we used the GRiSP board to actually test this, because you need the hard real-time operating system. Otherwise, you can't test it. But yeah, so that's kind of like another thing we did. And that's also some things we want to do in the future, that you really have an application system where you can write hard real-time processes. Like not nanoseconds, but milliseconds, it's fine. And actually what we observe is that the Erlang soft real-time, if you take away the operating system, it's much harder than you think. So it's actually quite well behaved for most use cases. So that's the dark slide again. Why is this dark? Okay, so how does this work? So GRiSP is actually not these hardware things. We call them GRiSP boards or GRiSP base, but it's actually a software stack which runs on all kinds of hardware things and can be ported. And it's made of 2 things, of the normal Erlang VM, vanilla, and there's a thing called Artems, which is nowadays you would call it Unikernel, but in the 80s when this was started, the word Unikernel didn't exist yet, probably. Unikernel is where you basically link the whole operating system as a library to your application, and then start it up with Unikernels, usually on a hypervisor, like directly without operating system. So we do this Unikernel-like thing, but we put the whole thing on hardware. So we link these 2 together, call them GRiSP, and put them on hardware. No operating system involved. So that looks like this. You have a traditional architecture on the left. You have normally your hardware. On top of the hardware is the operating system kernel, like the Linux kernel, for example. Then on the Linux kernel, the Erlang VMs run. In the Erlang VM, your application runs. Then you have other software on top of the kernel. And if you want to talk to the hardware, you need to go through a driver in the operating system, drop down to kernel mode, et cetera, et cetera, et cetera. In our case, everything in the red box is linked together. So you have your Erlang VM, your application. It's not linked together. The application gets loaded, but yeah, it lives in the Erlang VM. Then you have this RealTime library. Other software you also link together if you need some other libraries. And you only can have libraries. You can't have because there's no process per se. Like there's an Erlang process inside the Erlang VM, but otherwise you only have threads on the hardware. And if you want to talk to the hardware from the Erlang VM, you directly, basically if you call out into an if, you can talk to the hardware registers directly, because it's all just the memory image. There's no protection. And that's kind of like what embedded systems are built of, like small embedded systems. In our case, we have protection because inside the Erlang VM, processes get protected from each other. So everything you do inside the Erlang VM can't crash the system. It only can crash the process. Then we have like a runtime, which kind of like is a supervisor for all the drivers and the base drivers that come with the system. Speaking of drivers, that's kind of like one example, SPI driver. You have the hardware. Then in this case, we use a board support package, which is the library that is actually board specific, which knows where the register for the SPI is. So SPI is a very primitive synchronous protocol that's talked on a PCB between chips, basically, serial protocol. And then we have a very tiny C driver that's like 1 page of C code. So that's my goal, to make the C part as small as possible. And write all the rest of the driver, on top of the SPI API in Erlang, because then you can do remote code loading, you're in the shell, you're playing with your hardware, and it's a huge difference in embedded systems if you have a shell talking to the hardware. To make this all work, we need tooling. I will, in a moment, show you in the next demo how the tooling works. So this tooling is, at the moment, already Rebar 3 and Mix. So everybody can use their favorite tool because we refactored all the nifty parts into this GRiSP tools library, which then are used by minimal plugins for Rebar and Mix. The way this works, that we can actually link everything together, is that the toolchain uses the cross compiler to actually build a whole OTP. So it downloads the OTP from Ericsson, from erlang.org. It patches it with C code from your drivers and its drivers. So we patch the drivers all in, and a few other things like the startup code. And then the Rebar and the Mix plugin builds OTP, cross-builds OTP in the background without you doing anything. And then it makes a release with this cross-build OTP, and then you deploy it immediately, quite seamlessly. But quite a lot of things happening in the background. So now we already have CI/CD pre-building infrastructure. So whenever there's a new OTP, then at the moment we need to push a button still, but the plan is that we don't even do this. And basically we build all the versions of OTP, cross-build them, because the nice thing is the cross-build OTP does not depend on your operating system. It only depends on this board, so it will work everywhere. So as long as you don't need C code, what the plugins do, they see if there's the right version of pre-built OTP, and it will just download it and use it. Because then you don't need to install the cross-compiler library, so that's kind of like nice. So let me show you how this works. So to show you how the tooling works, I need to go to my laptop again. And something happened. Yeah, okay. So I'm trying to build a blinken light from an empty directory. Blinken light is the hello world of an embedded system. But usually it's much more work to make a blinken light, because you need all the stuff working together than actually hello world in normal programming language. So let's make an empty directory. So nothing in there. So all that's installed now, like the prerequisites that I did, the rebar plugin is installed globally. So I will do this with rebar, and because it's faster with rebar, because actually for this use case, rebar works better than Mix already. Kind of like overtook Mix in this case. Mix is a little bit more work, but it still works. And I'm an Erlang programmer, so I don't want to kind of like have you look at me writing Elixir code. That's not a nice sight. I always put dots at the end of the lines and do things because, yeah, you can imagine. So the plugin is installed globally, and rebar has a templating system, so you can actually have templates. And then you can do things like new GRiSP app, and we give it a name. Call it Blinken. And then there's another parameter, the destination. That's where we expect our micro SD card from the GRiSP board actually be mounted. And on a Mac, that's volumes GRiSP, if I format it with the name GRiSP, which I usually do. So yeah, it did something, it created a few files, and now we have a directory. That's kind of like a frame application. So you can already do a rebar 3 compile. Oh no, it wants to fetch something. Sorry. I need to go to a different. Let's go to the iPad. Because I'm still connected to this little critter here, and it's not connected to the internet. No? That's bad. Why doesn't it do this? Let me unplug this. Huh?
It looks like it's in the cache. It looks like it's good.
Oh, using cache file. Okay, yeah. Oh yeah. I forgot about the cache. Yeah. Cool. Yeah. So it builds because I tried this in a hotel room. But that's kind of like boring because it's not doing anything. So let's get me my editor, my sturdy MX, and then go into this directory, talks, MPEGs, LA, and Blinken. So that's how it looks. So there's a rebar config, which is pretty easy. There's a GRiSP section here, which has the thing. And so that's kind of like the source thing. And let's go into the application mode, basically, which starts the supervisor, and add some blinking there. So here, we need to kind of like get the supervisor. No. And then we call GRiSP, LED, flash, first LED. Which color do you want? Magenta. Didn't have magenta yet. 500 milliseconds. And then we need to return the supervisor. Actually, does it return OK supervisor? I'm not sure. Actually, this is superfluous. I just pick the supervisor, take the OK for granted, and just return it for sure, so I don't have an error here. So now we build this again. Yep, compiled, and now we deploy it. So to deploy it, I need a GRiSP board. Where's my GRiSP board? Oh, over there. Out of the box, like fresh GRiSP board. Comes with an SD card. SD card reader here, already plugged in. Put this in, and I really hope this is pre-formatted. This is upside down. So let's see, Finder. Let's see if it mounted. Yeah, there's a directory called GRiSP, and there's some stuff, GRiSP SD, I don't know what this is. Old stuff. Oh, let's actually delete this. RM -RF. Don't make a mistake now in front of everybody. What? Oh, there's a Reba 3 there. Oh, that could have been bad if Reba 3 would have an RM command. That's how, yeah, now it's empty. So, okay. So now we do Reba 3, GRiSP, deploy. And we need to tell it what release we want to actually use, because you can have multiple releases in a GRiSP config, and the version. That's kind of like the default version. Typo, no. So get the download area again, but it's cached. So it wanted to basically, there you see, it wanted to connect from S3 the pre-built OTP, but it's cached already, and it copied the file. It was quick. Did this work? Yeah, now we have blinking here. So yeah, this worked, you see. And now we need to eject the card, otherwise operating system complains. And then take it out, put it into the GRiSP board. And then I'm missing a cable here. Ah, that's darned. Ah, no, I connected it already. Come prepared. And we plug it into the USB port for power. So that's kind of like powering up now. And then we can actually watch it boot. No, that's the wrong window. So there's an open port. So let's start again. So that's, now you see it booting. And well, you leave it. The problem is the boot time is not very good. So we continue. So yeah, booting is boring. Don't want to see this. But it's still green. It's not blinking magenta. Problem is I don't, yeah, well, I see when it doesn't work. But you don't. Okay, back to Keynote. Okay. So you're the first to see this outside of our company. And others only saw this on video. This is GRiSP 2. I got it just before the conference. We're a little bit delayed. And I don't have nice pictures yet on the website because it just came, fortunately. So this doesn't actually work, so I can't show it to you because it's missing all these little wires because it's the first version. But I can show you a version that works kind of. But first, let me tell you what's the difference between GRiSP 1 and GRiSP 2 and why we did this. So GRiSP 1 and GRiSP 2, now I'm kind of like dogfooding my own shadow here. So GRiSP 1 was an Atmel CPU, which was a Cortex M7 ARM architecture. And GRiSP 2 is using an NXP IMX6 ULL, ultra low power, which is a Cortex A7, which is much more beefier than the M7. M is for mobile microcontroller size, and A is basically, it's almost a real core. It's still a single core. The clock speed is about twice as much as the GRiSP 1. It hopefully doesn't have a bug in the USB. Actually, the first thing we did is test the USB in this chip before we actually made any hardware with an evaluation board. It has double memory because you can't get them smaller. So this is super plenty for running GRiSP. The board type, this one is a fixed design, and that's a modular design. So you see this, can you see this? You see this little module here? That's basically a PCB mounted on a PCB. I have a picture that was close up later on. So because somebody, like for example, the guys with the accessibility thing, they actually made a baseboard with their sensors on, and then they made these connectors to basically shove in these PMOD connectors, and then little wires on the side, and that's not how you do it. So we made a modular thing that if you make your own, if you make an application prototype with the GRiSP board, and then you make your own board, you can just take the system on module and solder it on, and it contains everything that needs to run the Erlang VM. So all the hard-to-build parts, and then you just add your sensors and and actuators. So the GRiSP board has just SD card. GRiSP 2 has eMMC, which is kind of like a soldered-on SD card, and in addition SD card. It's kind of like nicer if you want to do like a small batch prototype because SD cards tend to fall out when it gets bumpy. But the soldered-on parts, I mean, they fall off also when it gets bumpy, but it's much more bumpy. You need much more Gs. I've seen capacitors falling off boards on a because they actually used it on a vibration disk. Like there's these vibration tables to test other hardware, and they put the measurement stuff on this, and then all the parts fell off the measurement PCB. It was fun. And then they complained about it. That's funny. GRiSP 1 only has Wi-Fi. So we thought, yeah, we have Wi-Fi, that's cool enough. We don't need Ethernet. But in practice, it actually kind of like was annoying because, oh, by the way, it blinks. 0 to blinking light, empty directory. So yeah, especially for tutorials or for development, you don't want to have to set up these little devices and then when you're connected to this thing, you're connected to the internet, as you just saw, this sucks. So yeah, we thought like, let's put on Ethernet too, and you see Ethernet. But we kept on the Wi-Fi. Also what we managed to do is we added a USB host. So you can kind of like add other USB devices, which we couldn't get in to the other GRiSP board, it didn't fit on. And we also put a secure key storage chip, and we put exactly the one that Nerves loves. So Frank told me, put this chip on, and I put it on. So there you can store your certificates, and then we also, oh, that's actually in the next slide already. So yeah, new faster modular hardware. So boot time will be much more faster just because the chip is more beefy, and we don't need to, so it's like, it's expected to be 5 times faster and use less power. That's why we also make a battery pack for it. We cooperate with the Nerves project because they were also kind of like delighted that we can have like a beam hardware thing where we control when it changes, because all these like Raspberry Pi versions and BeagleBone versions, they are actually hard to support. You need a lot of drivers, and then somebody got a weird version and it doesn't work. And if you control hardware and software, as Apple shows, it's actually easier because we decide when it changes. So yeah, we also want to kind of like use the firmware, the firmware update infrastructure from the Nerves project to use for GRiSP updates. So you can kind of like use both operating system versions interchangeably on the same hardware. Ethernet and Wi-Fi are already installed. So that's the thing that's the working GRiSP board at the table of the hardware developer. You can see it's a hardware developer because he has a Dell. Sorry. But it's kind of like funny, like our software guys all have Macs, and all the hardware guys, they never have a Mac because all the hardware tools, they only run on Windows or if you're lucky on Linux. So the thing on the screen behind this, the thing is booting, it's discovering the SD card, it's seeing the Ethernet. I think it already saw the Wi-Fi, I'm not sure. So they're just working on getting the first like drivers up. I have a more close-up. You see these little wires here. That's what you need that it works. And this board doesn't have them. That's why it doesn't work. So GRiSP 2. So let's rush a little bit to the rest of the slides. Future. Oh, it's a second enterprise. It's funny. So yeah, also space-themed future. Future is in space. So I have a little kind of like goal that I want to aim at much smaller hardware. Kind of like GRiSP got larger because we wanted to support Nerves also. And because it was not actually that hard and it doesn't need to be more expensive. But there is not only system on modules, but there's also system on chips. That's one chip which contains the CPU and the memory. And you don't need any external chips to do anything. You just connect sensors to it. So this is a much smaller kind of like device. And you can get those with like 8 megabyte flash, but you can run out of this flash and 1 megabyte RAM, which is kind of like tight. It's not like the 128 megabyte, but if we can run Erlang code from the flash, we can actually fit the system, and I measured this. Like the whole image, kind of like cut myself on the board, the whole image of the Erlang VM plus the TCP stack plus RTEMs is 2.5 megabytes. So we have 6 megabytes for beam files. That's kind of like plenty. So but how can we actually run Beam files from Flash? Because the problem is, if you load a Beam file, it's loaded into RAM, and then it's relocated to a different place in RAM. And all the little pointers inside are changed. Like atom table integers are kind of like the indices into the atom table are kind of like burned into the code. So it's modified a lot. It's transformed, relocated, and then the atom table pointers put in. And relocation means that all the pointers in the Beam file, there's lots of pointers in there, get kind of like added a certain offset to where it's actually done. And this even happens for the preloaded modules, because at first I thought, we use preloaded modules because there's kind of like 8 modules preloaded, because Erlang uses Beam files, it uses Erlang code to actually boot the rest of the thing. So yeah, this doesn't work because it's still loaded in RAM and we only have 1 megabyte RAM. So the idea is, and that's kind of like an ongoing project, convert the Beam files into ELF objects. Because an ELF linker, so a normal linker, can actually relocate stuff. There's a relocation table in there, and we basically need to extract all the relocation information of partially loaded Beam files and make an ELF relocation table out of that, and then a normal linker can actually relocate it to any place in memory. And then we linked it together with the Erlang runtime, because that's the thing we do. We link stuff together with the Erlang runtime. So why not let's link the Beam files also into the runtime? What do we get from this? All code is in Flash now. So we can run out of Flash. We can actually, on normal computers, we suddenly have a single executable. That's kind of like popped up on the mailing list now and then. Like I want to have like a single executable which I can send somebody, and they don't need to install Erlang first and whatever, and it just works. Kind of like an Erlang release is partially there, but sometimes it's more convenient, and like languages like Go, like make advertisements with that they can make a single executable which you can just put somewhere and run. And we can actually do this then too. And it will greatly improve boot time, not only for the GRiSP board, for anybody. So let's say Mix and Rebar are built like this. So all your build tool chains run much faster now, because booting up the Erlang VM takes some time, and loading all these little Beam files and relocating them. Many little files, reading is not the fastest thing on a file system. And that's the reason why the booting takes so long on the GRiSP thing. There's another little project. Basically, there's another kind of like Unikernel thing. It's called OSV. And there was a Erlang on OSV project, which was kind of like defunct for a while. And then my friend Rick Payne kind of like took the ideas from the GRiSP toolchain, kind of like looked at our toolchain, and adopted it for OSV. We are now working on backporting this into the GRiSP thing, so we can use our CI/CD stuff. And that means you can get a vanilla multi-core Beam on a hypervisor directly, because OSV is like Artemis, but for running on hypervisors. That's basically similar like the Erlang on Zen project, or now I think it's now called Ling. I don't know if they're keeping up with OTP versions. It's getting harder and harder. OTP is evolving, and they have a specialized version of OTP, their own, and that's kind of like not going well on the long term. But this is like vanilla Beam. So this gives you very quick startup on the hypervisor, milliseconds, and Erlang VM is spun up, much more less SSD. Yeah, I think I rushed over this. We are working on improving Erlang distribution, kind of like did a prototype for fixing the head of line blocking thing, and the OTP team kind of like liked this and implemented it for OTP 22 into the core. So there's no head of line blocking if you do Erlang distribution, which was one of the major problems. And our next thing is we want scalability. If you have any problem with Erlang distribution, talk to me, because we want to fix them all. We want Erlang distribution to be usable at scale, at the edge, in the cloud, everywhere. That's kind of the goal, like world domination for the Erlang VM. Well, speaking of world domination, so that's kind of like, this is not a joke, actually. I want the Erlang VM in space. This is the plan. It's not a short-term plan, but it's the moonshot project, basically, literally. Probably not the moon, but yeah. Yeah, so that's the end of the talk. You can pre-order GRiSP 2 now. We will probably deliver end of April or in May, if all goes well from here. So we have a delay. We want to deliver in October, but we need to change hardware developers and hardware manufacturers because our old manufacturer got too expensive. So we need to find a new one because we didn't want to kind of like increase the price. Yeah, www.grisp.org. We are on Twitter. And also we have this little thing. We have a live coding Twitch channel using GRiSP usually. It's running, it used to be running last year every Friday at 9 a.m. PST or 1800 Central European time. We did a kind of like hiatus over Christmas, which kind of like extended into January, kind of like too busy. And also we're kind of like thinking maybe moving it to another time. There is, on the website, there's a newsletter you can apply for. I can assure you we won't spam you, mainly because we're actually sending to few of those. We should send more because it's too much work. And we don't have a marketing department yet. So you can probably stay on the newsletter until we have a marketing department and they spam you. So if you move the time, we will announce it there, but we also will announce it on the channel. So there's a channel page, and it's kind of fun because I get to code. I usually don't get to code much anymore. And if I volunteer on the Twitch channel, I get to code for an hour or two. It's kind of like you see how the sausage is made. We do real stuff there. We either work on GRiSP or I work on my solar heating controller. So the whole solar heating controller was solely written on Twitch, including this bug I left in. Okay.